simulation application, and finally summary. So that's the, so it still doesn't work. Okay, this is backward. Next. How? Why just 2.9?
The screen's still not moving?
Just a 2, and then we go back to them. How do I go this way? Is it okay? It's not full screen. Can you see?
Yeah.
Okay. So classification. So we have the data xi or yi and sample size n. So the x is p features or the p predictors. So it's p dimension. Y is label. Okay. So we have k labels. So that's your data, and you try to use your data to do the prediction of the label of the new input the vector. Okay, so that's the, you build the classifier based on your data and try to predict the class of your input vector. An example, I give 3 examples. So your X is the gene profile. Okay, you want to predict what's the subtype of this patient's cancer. Okay, and you want to predict this email either is a spam or regular email using the vector of relative frequency of words in the email, or you want to do the imaging recalculation, okay, based on the screen, the green intensity, or the, if it is color imaging, you use RGB color values of each pixels in the imaging to do the prediction of what objects in this imaging. So this it is the problem of classification, also is called the discrimination analysis. And in the computer community, they're using this is type of supervised learning because they provide the label of your training data. So it's called the supervised learning. And in the high dimension data or the big data scenario, it means either the large scale, your A is very large, the sample size large, is your data matrix is tall, okay, the A is large, or it's very wide, the dimension P is huge, okay. In this case, your ultra high dimensional means this dimension P is much larger than N, even the log P is the magnitude of n power some omega. So that's the case of we need to dealing with, because this give us the challenge. The computation is feasible. Okay, you cannot compute what you want to compute, and also your model is have the very poor generalization performance. They can do very good for the training data. However, when they're doing prediction for the new data, they have the very poor performance, and your model have very poor interpretation. Okay, so you cannot say why your model doing good job on this prediction. So they have the model interpretation is very poor. So strategy to dealing with these challenges, we usually doing with this dimension reduction. So one way to do that, it is we form the new features. Okay, so they combine your feature together so that we only use a few features able to do the good job. So your PCA, principal component analysis, it's linear combination of your feature. You just use a few PCA, you doing this dimension reduction. The curl PCA is nonlinear, okay, combination, or saying those are combination your feature. So the new feature you combine, the new feature may lose interpretation of the original feature. So your data usually is connected by some domain expert. Those features have some meaning. So if you're doing the feature combination, the new feature may lose that interpretation. So the other way it is doing the feature selection. We still use the original feature, but we select the important, or it's called relevant features. Okay, so doing that, we need several goals in your mind. First, you need computational efficient. Okay, and you want to improve your performance and still keep the good interpretation. And this can be done by the two-step procedure. Okay, the first step is doing the screening. Okay, so we can quickly to screen out the importance features. Okay, screening using some importance measure. So we can reduce your dimension P to much smaller dimension D. Okay, filter out unimportant features. And doing that, lose low or just a little bit prediction power for your Y. So we still want to give very good performance for your prediction, and must be very fast. That's the first step. Second step, it is based on those candidate features, we do the final selection, okay, by solving some optimization problem. This it is more time consuming stage, okay. All the focus on it is screening the first step. So, or the goal, it is propose a screening process using or the Gini distance correlation. And the good things, I list those 5 things is for all the proposed procedure. And I will explain in the later slides to say what it means, okay? And the last thing it is they can be applied to individual feature screening and the group feature screening, which means your feature can be individually to screen out which individual feature important. Or if your feature are grouped together, I wanted to say this group of feature is important or not, we also can do, as long as you have the groups, okay? And or the notation or the presentation today, I will focus on the group of the features, because you can treat this individual feature screening just a special case of group feature screening, with each of group number of the number of the feature in each group is 1. So that's special case, okay? Now, so the group importance to do this, your predictors or the features has to be partitioned into R groups. Okay, so this it is, you need to have some domain knowledge to come from some expert to tell you your predictors or the features can be grouped into those R groups. Okay, so this P features group into R groups, and the I's group have the dimension QL. The L's group have the QL. So those dimensions of each group add together should equal the total dimension. And we assume this QL, it is finite, so each group is finite. And in the ultra high dimension setting, this number of group is much greater than N. And since this P is greater than R, so it must be greater than N also. And what we're doing it is we ranking this group, okay, L's group XL, and by this Gini distance correlation with your response category Y. Okay, now I need to tell you what is the Gini distance correlation. And so your Y is category, and this is your distribution. Okay, Y equal LK is PK. Okay, and for your X, okay, L's group has a distribution of FL, and their characteristic function is psi L. Psi L is just the Fourier transformation of the density function of your XL. And the conditional distribution and characteristic function of XL given Y equal K, this is our other rotation, FL, K, and psi K. The Gini distance correlation between XL and Y, it is kind of L2 distance between your the characteristic function, conditional characteristic function, and the marginal of characteristic function. So it is weighted, okay, weighted with this weight. So this says just constant, depends on your dimension. And this PK, it is the distribution of your Y. And you will say this, it is square distance. So it must be greater than or equal 0. And if it is 0, which means they are independent because the conditional characteristic function is the same as the marginal. Okay, so equal 0 if and only if that's they are independent. The popular distance covariance, okay, usually they're doing with two numerical variable, X, L, and Y also it's numerical. And it is proposed 2007, it becomes very popular. And in all the previous paper, we extend that Y to be category. So we found this distance covariance for your Y's category, it is PK square here. Okay, so they are closely related. And when the QL is 1, it's one dimension of X, and that's covariance can be writing as the distribution function, square, L2 square of conditional distribution function and the marginal distribution function. Okay, and I list the other 3 methods we will compare later. Okay, so the distance correlation is PK square here. Okay, and the mean variance they're using, instead of respect to the X differences square to distance, they respect to the CDF. Okay, it's rank based. Okay, and the AD is just Anderson type of quantity, and they standardize. Okay, this it is they give more weight on the tail of your axis. So they give some weight on each of X. Okay, so you will say the PK square for the distance here, the PK square in here give the problem if your data, if your Y label is very unbalanced. So the PK square will dramatically reduce the inferences from the small class. Okay, so for example, your PK equal 0.1, the contribute of this class will reduce to 100%, 1.01. Okay, so that's the problem of distance covariance when they're dealing with unbalanced case. We will say simulation later. Okay, so that's the problem for the distance covariance. Yeah, so you will say the similarity and the differences of those approaches. Okay. If you just estimate for this, it's not easy because you need to estimate, if you wanted to estimate those from this representation, you need to get the CDF. It's not easy, okay? But the good thing it is, we have the other representation, okay? This representation is called the Gini mean differences representation. So this Gini covariance can be writing as the delta L minus this sum of PK delta L, what is the GMD of the conditional distribution. So this it is just you randomly select the two random variables from the distribution. Okay, you find what is the distance, expected distance from these two random variables. The it is multivariate Gini mean differences. Okay, so you have your from the marginal, you draw two random variables, find their distance. Okay, and for the each conditional distribution, you draw two random variables, you find their distance. So this it is overall Gini variation. This it is within group of variation. So this it is overall minus within. That's give you some type of between the variation. Okay, and the correlation, we just standardize your covariance. Okay, standardization, it is just divided the total. So this is a between the Gini variation over the total, have the very nice interpretation of this quantity. Okay. And this correlation is between 0 and 1, standardized. And if it is 0, mutually implies the independence. So that is why we wanted to use this quantity, okay? And easy to calculate. So this it is why we how we calculate. And we have the data, and all the data can be writing as this subsampling of DL. The DL, it is Y equal just class K, okay? And your PK is just to use the number of your sample in your class K over the total, and your correlation is just to put your hat in your delta, okay? So everything you put a hat, give your estimator, and your delta L, it is the average. Right now you need two average, so it is U-statistic in the overall data. And this is just in the subsample data, okay? So those are U-statistic, okay? And next, let's go back to the screening problem, okay? So you first need to say, what is the mean of important features? Okay, so this it is what we come with. If you given your X, your G is conditional distribution of Y, okay? And your, we call it the importance set or the active set, it is the index of your feature, group of feature. This conditional distribution given X functionally depends on your group, okay? And in active set or inimportant set will be the index of your group. It is this conditional distribution does not depend on this group. So if we put this index together, you get the active and the inactive predictors. Or the object is to identify A or the XA. Okay, so that's all the screening procedure want to do. And what we're doing is we select important feature put into your A. Okay, so we select the important feature with large sample Gini correlations, PL. If this is large enough, we put into your A. So we estimate your A by this A hat. It is your GD correlation. It's larger enough, okay, larger than this quantity. This quantity able to, as long as your as your n goes to infinity, this number can goes to 0. So it's larger enough. When your n it's large, this can be larger than some number greater than 0. Okay, and this capital K, kappa, will be threshold to will be defined in the conditions 3. When we derive the theoretical result, we need some condition that it is showing over there. And in practice, because this one it is we don't know C, we don't know kappa. Okay. In practice, what we're doing it is we given some desired dimension D, which is smaller than n. Okay. And we select your group with this correlations among the top D largest. Okay, so we ranking your feature groups by the GD correlation, GD distance correlation, and we choosing the largest D. Okay, so that's it is in practice what you're doing for the screening. And to develop this theoretical result, we need these conditions. The first condition is just for the distribution for your Y. Okay, so this PK, the smallest and the largest will be the same magnitude. And we put the number of your class of your Y, put sometimes we have the sub index n in here, sometimes we don't. Okay, in here it is means this number of the level of the category can be increasing as your n increasing. So this you are able to dealing with divergence number of class, right? And your first condition is just your smallest, your PK is the smallest label and probability, and the largest probability of class. It is not done. It is same magnitude, not dominated by a few classes. Okay. Second condition is dealing with your the tail. Okay, this it is not small. The what is this it is this condition is just proposed to let all the proof to be easy, may not to be the minimum or the conditions. Okay, so the X must be sub exponential tail probability uniformly in the group and in the class. This is what it means. So expectation of this must be finite. So give some, they will converge, the X distribution will converge in the exponential tail, okay, decreasing to 0 fast enough to be this. And this condition including your normal condition, the normal distribution follow this one, and some exponential distribution like the Laplace distribution will follow this, satisfy this condition. Okay. And number 3, it is for your class, okay, for your active class, the important features. Should the row L must be have some lower bounds, okay? So this means your important feature must be have the correlation requirement for the correlations, minimum correlation requirements for the active class. Okay. So this is 3 conditions. The first 2, if you satisfy this 2, Okay, we have this uniform convergence in the exponential decreasing, in the exponential speed for your rho L hat to the population rho L. Okay, so the convergence rate, it is exponential fast and it's uniform convergence, okay, on all the class. And this gives us the way, some rule for the class, for the number of the group able to catch up of exponential of your n. If it is smaller than this magnitude, then you are able to allow the number of the group, okay, that many of number of group, okay, to still have this converge to 0, okay. And the tau, it is your number of the class of your category class. Okay, remember what is those quantities. And if this it is proved, we will see the idea of how to prove this, okay, later. And with some simple arguments, we have this sure independent screening property. Okay, so this it is, if this it is the Bn, it is subset of those. So the probability of your Bn, you already prove the exponential convergence rate. Then the probability of your A, it is your true important set. This is your A hat, it is your estimate set. Your estimate set containing your true important sets will be greater than 1 minus this, will goes to 1. Okay, so which means you choose your important feature content in your selected set with probability 1. This it is the sure independence screening property. Okay, so we can establish this property. And if your Kn is fixed, the number of your category is finite, so your tau is 0, then we can improve some term, okay, some terms go away. And then if you can choose in this beta to make these two terms a same magnitude here, then your beta chosen to be 1 minus 2k over 3, then this term is go away. So you can have more optimal order to combine these two terms together. Okay, and now I will talk about the other property. It's called the ranking consistent property. This property is more stronger result than the sure independence screening property. And they require a stronger condition. This one, it is condition 4, talk about the minimum of the correlation in the active set and minus the maximum in your inactive set of they have the gap between those two sets of correlation. Okay, that's basically says. So the active set, the correlation, smallest one, the bigger than the largest in the inactive set. Okay, so the population have some small gap, have some C3, have the gap. And the ranking consistent says the sample, okay, if you based on your sample data and your sample achieve almost surely this it is greater than equal 0. So the ranking your importance feature, okay, always no lower than your inactive features. Okay, makes sense? So this it is more strong result than the previous sure independence screen property. And almost sure you need the borrow containing lemma to prove that. Okay, so yeah. Idea of the proof. The mean thing, it is dealing with GD covariance. Okay, the sample GD covariance and what is the convergence rate. And the correlation, just to the bottom, it is U statistic, and we're dealing with that U statistic here. So they have the same exponential convergence rate also. So we're dealing with this. First, we partition into 3 parts. The first part is U statistic, okay? Second part is pk hat times the other U statistic. The third part, it is your pk hat minus pk. This is just some constant. So it's easy to have the exponential rate for your pk hat minus pk because it's available, okay? Very easy to prove that. The problem, it is U statistic in here, the convergence rate. If your distribution is finite, okay, your x, it's in the support of x is bounded. This is easy, okay. They can do the Hoeffding decomposition, Hoeffding inequality. You can use it to establish that converges, okay. But or the xi, it's not the bounded. So to dealing with this unbounded U statistics, and we into 2 parts. Okay, the first part is truncated, is to be bounded, and the other part is your tail. Okay, your h is greater than m. We should carefully choosing later on. Okay. So your first part is easy, okay? Hoeffding inequality, you can prove this R1 converges population R1, okay? Second part, it's unbounded, is tail part, and use your condition 2, okay? Your condition 2, you have some requirement for your tail decreasing quickly enough, and your M you choosing so that they still have the convergence rate. It's exponential convergence rate. Okay, so that's all I think the most important technique we need to go over this part. Okay, and now I go into the simulation study and application, and we conduct the several simulations, as this one just include just one of those 4 simulations. And we compare 5 methods. This is doing individual screening, so we can do in this R square. It is ANOVA R square, okay? So it's X is 1 dimension. We are able to find the R square. And MV, as we said, that's the mean variance introduced before. AD, okay, distance, okay, and or the Gini, okay, 5, and or the dimension is 2000, okay, sample size 6 for your k equals 3, okay, 3 category, and for k equal 10, we're using sample size 200, and your Y have these 3 distributions. One is balanced, so every class have the same probability 1/k. And slide the variance, it is the largest PK is about the twice of smallest PK. And heavy unbalanced, like 5 or 6, the largest PK is 5 or 6 times of the smallest one. So we consider these 3 cases. And or the model is just the location model. Given your Y from your K class, your XI have the mean mu K plus some error, okay? So your mean K, it is in this way, only have your mu K equals 3, the other is 0. So 3, the K class have the different location, okay, plus some error for your X. And your arrow have the normal and it's T2. So in this case, we have active predictors. For your K equals 3, we have first 3, X1, X2, X3 are active predictors. For the K equal 10, it's first 10 predictors is active. Okay, and we repeat this 500 times, you're able to output some criteria. And we're using minimum model, the size, minimum model size to as all the criteria. Okay, so minimum model, it is the smallest model contain all active predictors. So you ranking your individual features and choosing your model so that all your active predictors in your model. So that's it is one way we do, and we output the median of minimum model size. Okay, and we also output the robust standard deviation of minimum model size. Okay, and we're using interquartile ranging over 1.34. So my students in the robust statistics know why they come from this 1.34. Okay, right? And the other way it is, we're choosing the model with a fixed D. So this is usually the case we're doing in the practice. Your D is chosen to be N over log N. Okay, and with this model, we find what is the selection probability of each active predictor, or what is probability of including all active predictors. Okay, so this is a result. This is for your epsilon from the standard normal, and they have the three cases: balance, slight balance, and heavily balance. And so the k equals 3, the number of the predictors, active predictors 3. So we should expect 3. It's all the good quantity. And the probability should be equals to 1. So in the case here, everybody doing good job. Okay, perfect job. For the unbalanced case, heavily unbalanced case, distance fell out. Okay, the reason because the first class have the very small probability decay, then the pk square will much reduce their identification of x1. So that's it is come from the limitation of the distance correlation. For the k equal 10, and doing good for the balance case, slight balance, slight unbalance, except the dt has a little bit problem for this one, but still okay. And for the unbalanced case, R square still doing good, or Gini correlation is doing good, but have the larger variation, okay, than your R square. The R square doing best because it is the linear discrimination analysis, okay, only the location difference with the error is normal, so R square is optimal, it's best, okay, and all the method is close to the best one. G2, the first, you can thinking the R square will fail, okay, that we're showing here. This it is the k equals 3, they have the 5, 26, because the heavy tail, the R square based on the variance, they have the even the population variance doesn't exist, okay, and all the gene is still doing good, 3, 3, 3, okay, and for k equal 10, or it's good, okay, until the last one, but still the best among all the method concerned compared, okay. And that's the simulation. What time right now? Okay.
5 more minutes.
Okay, so I will go quick, talk about this real data analysis. For this one, we're doing the group screening, okay, and only 2 method available, okay. So MV, AD, R squares only do the individual screening. So we only compare the distance correlation. And we use the breast cancer gene data, and the dimension, it is 17,278 genes, and the patient 506 patients. And the K equal 4 subtype of cancer, okay? And for this one, why we choose this data? Because they have the golden standard, okay? So those 48 genes, okay, we call the PAN, okay, which is in all the gene, okay? Those, in fact, is PAN 50 genes, but all the data only contain 48 such genes. So we call the PAN 48. Those gene already put its golden standard to for the breast cancer. It's come from the dominology, the doctors, those people to identify those 48 genes are good standard, the golden standard for this cancer. And so what we're doing it is, besides remaining the other, this many of the genes, we group together, okay? So because we don't have the dominology, how to group them, so we're doing manually, okay, to form some groups, okay? So we have the 4 ways to do the groups, okay? The first one, it is your data give us, they have the ordering of your genes, okay? So we're using that's original ordering to give the group. So the first 50 genes, that's the group 1. The next 50 genes, that's group 2, etc. And we're also doing the random groups. So we have the random 1, it is get the random group, random without replacement. And random 2, it is with replacement. And the 4th method of group, it is we first re-ranking individual gene of this using the GD correlation, and we give the ranking, okay, from the highest to smallest. Then the first group is the top 50 genes, okay. Okay. Then the second group with second integer. So we fall in those groups by those individual or the marginal ranking, okay. And all the data, we have the 80% randomly to be the training data, 20% to be the testing data, and we use a random forest to do the classification to give your performance of your choice, okay, of your select model, okay. And we repeat 100 times. So each time we randomly choosing 80% of training and 20% of test. So we repeat 100 times. And this is the result. So the PAN 48, this is the gene. This it is what is the group correlation of the GD correlation. And because this is calculated for your training data, so we have to repeat 100 times, so you can calculate the mean of your correlation and standard deviation. Okay, and this is a distance correlation and standard deviation, and those it is output the correlation with highest among the groups. Okay, so if you look at those numbers, your PAN 48 have the highest GD correlation, and the distance correlation, the PAN 48 has the highest correlation. So in this case, if you choosing the group, the PAN 48, you will select by both of the methods. Okay, so that's the first thing I want to say. This it is PAN 48 is really selected by the both method, and then using those selection and using the random forest to compare the performance of select the group. And this it is different methods about what is the training classification error. This is a test error. Okay, Probably I will show you the plot. It's easier than the table numbers. Okay, so we put into the random forest. Okay, for each of the selected model, the PAM48 give you smallest the error. Okay, smallest classification misclassification error. Okay, and in here this is on the test error. So the PAM48 is give your smallest one. And for the marginal, this marginal really help for all the group, okay, because they produce the second smallest classification error in here also. And the blue is all the Gini, and the purple one is the distance. So you can say, if you compare with overall, or the Gini is better, the selected model is better than the distance. Okay. Just last slide. Okay. So model free, because we don't have the assumption on your what is y and x, what is model. Okay. And sure independence screening property, we already proved that the ranking consistent property also hold, and ability to handle divergence number of category levels. Okay, we show that tau can be greater than 0. Okay, your kn, it's n power tau. Okay, and they apply to the individual feature screening and grouped feature screening. For the individual feature screening, this is computation and complexity. P is your dimension, n log n. Okay, for the grouped feature screening, R it's the number of the groups, and square. So that's increasing your computation when your n is large. Okay, but usually n is not large. Okay, so the group feature screening is still okay. Okay, so next it is. Okay, so what I want to say it is artificial intelligence is a very hot topic right now, but the core material, it is statistics. Okay, so people, it is already Chinese old saying, old wine in a new bottle, but we need to name those new bottles. It's really important. Okay. Yeah, next one, it is references. Okay, I'm done. Question.
Thank you. You had a question from Louis May in the chat.
Okay, so let me ask, do evaluate how XY? Okay, so let's go back. Yes, my answer is yes. You can do the correlation. It is more good quantity to say how and why are more correlated. So I think the correlation
Do we have any other questions here? Everybody is so calm. It seems that we are at a funeral already. Okay, so today it seems we are finishing like 5 minutes before the end of time, and It's time for us to thank everybody.
I'm sorry. I think I'm kicked out.
Oh, no, you are still with us.
Oh, really? I
Yeah.
saw its connection. Oh, one more thing I need to emphasize. This is a joint work with Unisom. I'm sorry I didn't mention at the beginning.
Welcome, welcome. Okay, I was just asking.
It's published already, right? Yes.
It is submit, just submit.
Okay. Okay.
All right.
Mhm.
Hopefully, in the next months we will be able to discuss what you were talking about.
Okay, yeah. So
How to mix these things with what I am thinking about.
okay. Mhm. Thank you, Uni. Thank you, Home. Okay.
All right.
All right.
If there is no more question, then thank you very much to the presenter, and thank you to everybody who had time to sign in online with us today. And Youngli, please, when you have time, do continue to visit us. All right.
So yeah, bye. Thank you all.
Thank you.
Yeah.